In this presentation, we're going to have a look at some real malware analysis. So an important element of this is really to understand all the different code types that are actually involved, from high-level language into intermediate language and then into the machine code. There aren't too many taxonomies around for malware analysis, but we'll try and develop our own and see if we can actually try to classify the different types of malware. Then from there, we'll look at the basic methods that we can use to analyze our malware, such as static analysis, dynamic, and also code analysis. Then, sometimes what we have to do is to look at the actual files in some detail. So we'll have a look at how we forensically analyze a file, and for this we'll have a look at the flash file format. Then we'll look at some real malware as it runs and how we can actually identify the problems that it actually causes. And finally, we'll have a look at a basic exploit kit to see how real malware is actually written. Okay, so we have various different types of code that is used to run software, but all of them will run some sort of executable code on the hardware. Unfortunately, it's very difficult for us to be able to understand the ones and zeros that the machine uses, so we normally use a high-level source code. Normally, what we have is a high-level source code, C++, Fortran Basic, and then that's then compiled into our machine code, and this is known as object code. The object code can't be run on its own because it has gaps in it, such as being able to interface to the keyboard or to the display. But it's a small part of the code, and then when linked together with some static libraries or other object code with a linker, we produce our portable executable, which can be run on the system. When we run it, it runs as a process, and then we can debug that process with a debugger. Or from the exe, if we need to reverse the code back again, we can use a decompiler to get the original source code. As we'll see later, malware writers like to scramble their code, so it makes it very difficult to get the code back again. Often though, or increasingly, what we have is that we have a lighter exe, which doesn't have as much object code, and calls the object code that it requires, or the code that it requires, through a dynamic link library. So with this, when the process runs, it hopes that it will be able to get access to a DLL for the additional code that it actually needs. This on a Windows system is often in the Windows System 32 folder. So for that, we can compile directly to a DLL, and the DLL can then be called by the process. The advantage with this is that we can update our DLLs on the system without requiring the whole exe to be updated. The problem with this though is that we can have what's called DLL hell, where a certain exe doesn't bind very well to a new DLL. Another method that we can have to produce our code is to start from almost a machine level or an assembly language level. With this, we use an assembler to convert this assembly language level, such as move, add, and so on, into our machine code. And we'll see later that sometimes malware writers write at this level so that they can obfuscate what they're actually doing and run code directly on the machine. The other type of code that we have is a high-level source code, which is interpreted. So languages such as BASIC, COBOL, Lisp, Python, Ruby, ASP, PHP, JavaScript, and so on, all use an interpreted method where the code is run at runtime on an interpreter. Then it's up to the interpreter to produce the code that's required to be run on the machine code. Advantage with this is that it can be machine independent, where this tends to be written for the machine. The different types of code that we have, this is the normal type of code. High-level code, C++, is compiled into either 32-bit or a 64-bit object code, then is created as a portable executable to run on this operating system. Problem with this is that it binds directly to the hardware and to the operating system, and we can't really move it to another system without special software. Also, we just need one piece of bad software, and it can hog the CPU, memory, and so on. Another type of code that we have, and one that's increasingly used, is to be able to run our code with inside a framework, such as the .NET framework or the Java framework. With this, we install the framework into the operating system, and it's up to the operating system to convert from an intermediate format into the actual hardware requirement of the system. So for this, we have our high-level codes, C#, VB.NET, Java. We then compile it into an intermediate format, which is a near machine-ready format as possible. The framework then converts this intermediate format into the format required for the hardware. This will obviously be slower than this type of system, but it means that the code can be checked and bad code doesn't affect the rest of the system. We also can make it portable, where the same executable can run on different types of hardware, such as we can install a .NET framework onto Android or into Mac OS and onto Windows, and then the same executable can run on each of the operating systems with inside their own .NET framework. Overall, in a Windows machine, we have two main levels of privilege. Ring 0 is where all the kernel drivers are. So when a rootkit is installed, it will be installed into this level, which gives it the highest level of privilege. Most of our application programs and other DLLs run in Ring 3. Increasingly, what we do though is that we run with inside a virtualized environment. So the operating system doesn't run directly on the hardware. We run it with inside our virtualization infrastructure, such as VMware. As we'll see later, this is where we run our malware. We do our malware analysis so that the system doesn't affect our own base system. If we have code that's written for another type of hardware, then we can use an emulator to be able to convert from the machine architecture that the code is running, such as for a Cisco iOS device or for a ZX Spectrum even. We can take the executable here, and the emulator will then convert this code into the required code for the hardware. And the last type is when we have some scripting, and with this we have an application which runs some scripts, such as for VB with inside Office, JavaScript with inside a browser, and Adobe script with inside Flash and PDF. This can cause us many problems, as we'll see later, as a malicious script can run with inside one of these privileged applications, and it can cause a problem on the system. So let's see if we can define a basic taxonomy for malware analysis. Okay, so this is quite a simple one, but it will at least allow us to be able to classify our malware and see if we can actually determine its operation. So in this case, a malware has a certain classification and is distributed by a certain method. So the distribution method might be through JavaScript, through Flash or PDF, or could be through a Trojan method. And this will have certain observable events for the distribution. As much as possible, the malware writer will probably try to hide some of this, so they will try to obfuscate, could be changing the code and so on for the distribution method. And then this will have some sort of system compromise to be able to stay resident or persistent on the system. And we can then find the malware using some observable persistence method. So it might be in the registry, might be files on the system, might be processes that are actually run. But again, the malware writer will probably try to obfuscate, try to hide, try to change so that the scanner doesn't pick it up. And then the malware is then triggered by a certain event. It could be by a user using a browser or pressing a certain key or logging into the bank or something like that. And then what we see then is observable attack methods. Might be to delete files, to be able to steal data and so on. So there will be a certain attack method which then results in some damage for certain objectives. Okay, so this we can see here there's a classification, we have some distribution method, we have some way where it stays persistent on the machine, it has some trigger, it then has some attack, it does some damage, and there is usually some reason behind the malware in the first place. So first let's look at some classifications of malware. It's quite difficult to really classify them in any great detail because there are so many different types, but let's see if we can put them into certain classes. Okay, so one of the first ones that were created were viruses, and with viruses they tended to replicate themselves and were there to really try and spread as much as possible. But it was generally a piece of malicious software that did something bad on the system, maybe tried to steal data or even delete it or change it in some way. Then we have malevolent worms. In this case, a worm will try to exhaust the system, such as using up too much CPU or network bandwidth and so on, and will generally compromise the quality of service of the overall network. Then we have Trojan horses. The Trojan horses, generally the users are tricked into thinking something is valid, and then a piece of malicious software is then run in the background, which can do damage. Then we can have backdoors, and when the backdoor software has been written so that there is an intentional hook that someone can get into the software and compromise the system. Then we can have some sort of exploit. So there might be a problem with inside Adobe Reader or Flash or even within Windows or a browser, and the malware will exploit this weakness to be able to cause a compromise in the system. And then also we're increasingly seeing what's called ransomware, and in this case a malware writer does something to the system, such as with CryptoLocker, where it might take lots of files and then encrypt them, and only by paying the malware writers back some money, then they will be able to decrypt the files. Okay, so this gives us a basic sort of classification of the different types of malware that we'll look at. Later on, we'll look at an exploit on a system using Adobe Flash. So let's have a look at some real malware analysis. So often what we'll do is we'll analyze the malware statically, dynamically, and then to look at the code. Okay, so the first method that we use is to look at this basic signature of the malware to see if it is well-known malware, maybe a day zero, or it may be a well-known one. So we usually use something like VirusTotal to be able to scan for a piece of malware to see if other virus scanners have actually picked it up. The other way is that we can look at the hex view to be able to see if we can see certain strings inside the malware. Okay, so let's have a quick look here. Okay, so we'll just choose our malware here. So we're running with inside XP here, and we have a zip file with the malware, and so we'll just scan it, and it's been scanned before. So 42 out of 47 scanners have identified this as possible malware, and we can see here's the antivirus scanners, and each of them calls them something differently, but this should be all the same type of malware. Some of these I've not identified at all, which is a bit worrying. But those are the scans there. So we can take a hash signature of it to be able to identify a certain file, because it might change, but it can still stay the same in terms of its execution. And we can see with inside there, that's the file that we have identified. Okay, so this will give us some idea whether this is a problem. Then we can look at it with a hex viewer to see if we can actually identify any strings with inside it. Okay, so we can have a look through and see if we can identify anything. The MZ is a standard file starter, magic file number for an executable, so that's not really giving us too much away then. But we should be able to find a unique string that we can actually take off, a hex string or an ASCII string, to be able to identify if the file exists on the system. And we might be able to scroll through and find some things. Sometimes the writer actually leaves their email address. We've got some things here. There's a version number in there. There is a company name. It's not really given too much away there. And there's a product name. Again, it's not really given too much, but that might be enough to be able to identify the malware on its own. Okay, so we can also look at the zip file with the exe in there, because we might be able to want to detect this with our intrusion detection system or our email system. So we could take a capture of that. Okay, so that defines our static analysis. Next thing we might do is we might want to do a dynamic analysis. So with the dynamic analysis, we've got a few different methods that we can use. We can do a file integrity check. So we can use something like our integrity checker. We can check all the files on the system and see if they've been changed. We might look at some file monitoring to see when we run the malware what files are actually changed, so we can use procmon for that. We might look at the registry to see what keys are changed with inside the registry when we run the malware, what processes might run when the malware runs, and then we might want to monitor the network to see what network connections are actually created from the malware. So the first thing we'll do is we'll show how the file integrity checker can actually work. We'll show a basic example of that. So in this case, we've downloaded the FCIV program from Microsoft, and this will create a database of hash signatures that we can check against. So let's see if we can find our VM. Okay. Okay, so we kept it quite simple. We just downloaded this FCIV package, created a very basic batch file. So we're going to create a database of SHA-1 file signatures, and we're going to scan the whole of the system. -r is recursive here for all text files. We can do it with any file, but we'll just make it text files just now, just to illustrate it. Then this will then list those file signatures, and then finally we'll change a file and then see if it detects it. So this line won't actually run just now. Okay, so let's generate them. Okay, so that's found all the text files on the system. Okay, and there's all the SHA-1 signatures for it. Okay, so what we'll do is we'll go on and find one of these text files and we'll go and update it. So this could be the malware that's doing this. So if we change it now, then hopefully we've created a tripwire. And then we'll just run this last line. And hopefully it's detected that file being changed. Okay, so this is similar to tripwire, where we would create hash signatures of all the files on our machine, and then we'd look to be able to detect it by running it again and looking at any changes that had actually happened on the system. So the other types of dynamic analysis we can do is file monitoring, look at the files it's creating, look at the registry keys it creates or deletes. We can run snort and wireshark to look at the network activity, and we can also look at the process monitoring to see what processes and threads it starts up. Okay, so let's run the real malware here. So the first thing we're going to do is we're just going to check that we have no network connection. And what we'll do is we'll make it a private address. Okay, so we'll make it 10.0.0.1 for this IP address. The gateway is at .2 and then the DNS is at .3. So let's check that we have no network connection. Okay, everything's fine there. And we'll just check the IP address again, so it's non-routable. Everything's fine. So what we'll do is that we'll start up Procmon. Process name we're looking for is dq.exe. Okay, so this is going to monitor our registry, file activity, network activity, and processes. Hopefully for the little program that will start up, and we'll also set up Wireshark. To see if we can detect some network activity. Okay, so everything's all ready to go. Okay, so the malware that we have is here. Okay, so it's a clean system. So when I run it, we can see nothing really seems to happen. Although when we look over here, lots seems to have happened. Okay, so this is showing us there's the process started, creates a thread. Okay, and then it does a few things there. It then tries to create a file in Windows Prefetch. And this is all its activity here. So we can see then it starts to look at certain registry keys. Okay, so quite a significant one is in this one here. We'll have a look at that in a little minute. So as it runs through there, it's opening up a few. So there's software, Microsoft. Having a look at a lot of the keys there. And here we go here. It's created a file in there. go. So it tries to create this file here. It says path not found. And then what it does is it goes and creates that folder. Then it actually creates the file after that. So there you go. So it's now created a file, and if you remember the name of that file, we'll have a search for it in a little minute. So the first thing we'll do is we'll have a look at the registry, because that's obviously the place that it will go to discover some things or to start itself back up when the system is rebooted. So we could search the procmon for this, but actually we can usually go and find it in the current user, software, Microsoft, Windows, current version, run, and there we go, there it's them. So you can see there the program, when it restarts, runs from here, will run this little program again, which means that it will persist on the system. So we can delete that registry key if we wanted. So let's have a look at the other file that it's actually created. So it's in Recycler. And just see there's nothing else in there. So then we'll go in there, and there's nothing there. But if you look at it, these are hidden files. Can we erase them? Looks like they're erased, but they're not. They're still there. And the reason for that is that they've been set to be system, hidden, and read-only. So we've got to go in one at a time and change the attributes. So that one we can now delete. So we'll only have one. Okay, so the attributes are this one. Do the same again. So it won't come back. And we can't delete it just now because it's read-only. So what we've got to do is we've got to go and reset the read attribute on it, and now we'll be able to delete it. Okay, so that's it deleted. So let's have a look at some of our network traffic. So we can see here this what's really happening here is it's doing a name query on this domain here. So we'll see in a little minute that what it's actually trying to do is send spam. So you can see there that the malware is trying to find the DNS server. That was .3. Doesn't find it, so it does an ARP, does a lookup for the Microsoft name server to see if it can actually find it. Okay, so it's continually trying to get out onto the internet to find this server here. So what we'll do is we'll just quit that. Should be fairly clean now, but one thing that we can do is we can go back and we can get our snapshot back to go back to a clean image again. So what we'll do now is we'll have a look at what this malware actually does. So this is a capture of when the malware was actually given a network connection. Okay, so you can see here this is the capture from it, and there's what we've seen before. So this is when we have our network address of 10.0.0.1. So what we do is that we allow the bot, the malware, to be able to connect, and we should see that happening in a little minute. Okay, so somewhere around here we are now connected back onto the internet. Okay, so there is a DNS query. It is then able to find the IP address, and then it does a connection. So it's resolved it to 217.23.2.159. Okay, so there's the SYN. This is our first connection after our successful DNS. So what we'll do is we'll follow that and we'll see what it tries to do. Okay, so it's connecting to what it thinks is an SMTP server here. So it's obviously looking to spam. So it does a hello to it. This is the server that it's trying to spam, but it doesn't actually get connected. It tries another one. Again, it doesn't get connected. And so you can actually see that this is trying to spam. It just continually keeps trying and trying until it can get a connection and send its spam. Okay, so that's shown an example of our malware analysis. Another thing we would often do is to do netstat -a to see the ports which were open up on the machine before and after. Okay, so this is back to our clean image here. Netstat -a will actually give us which ports, and it could be that a new port has been created. Another type of analysis that we might do is we might look at payload analysis, because we obviously want to be able to detect when a bot is or malware is actually arriving at our machine. So let's look at an example of an email coming in on SMTP port 25, and we can see here there is the malware is in a zip file, and with a zip file with an email message SMTP, what we have is we have MIME, which breaks the message up into a number of different formats. And what it does is it will take any binary and convert it into base 64. So here we see the zip converted into base 64 format. So if we want to detect this in Snort as an email, we would detect this as part of the payload, because that's the base 64. So it's not the zip file. The zip file is converted into a base 64 format. So if we want to be able to detect it, remember that it's not the zip file, the signature we're detecting for email, it's the base 64. So what we'll do is we'll send it as an email attachment, we'll run snort, and we'll see if we can actually detect it. So in snort we have alert.ids, and hopefully when we send the email we'll be able to detect it. Okay, so what we've got set up here is, so this is Windows 2003 VM. We'll just have a little look to see what the IP address is, and this should have, so it's 47134. 47134. And we should find that this should have SMTP running, as it has. So running the service. And what we'll do is we'll connect this back onto the network. So now it should get its IP addresses from VMware and connect to the same network. As the other VM. Okay, so just see if the other VM is alive. 47.134. That's fine. So we're going to send it as an email message. So if you want, we can actually have a look at the Wireshark trace. can actually see the email message going out, just to prove that it's base 64. Right, so let's have a look. And so I've just created a very simple rules file here. So I've taken a sample of the base 64 and this is what it is. So then let's have a look at the interfaces that we have, and I think we're on interface 1. Okay, so that's it now waiting, so Snort is now detecting the network packets. So then we'll create a new account. Okay, so we don't really need the pop, but I'll set it up anyway. It's the SMTP that we really want. Okay, so let's create our email message. That's our malware. Then send it. Okay, so you can see that it went through quite quickly then. So there's our port 25, there's the message. Okay, so that's the standard email message for sending, and there we go, there's the base 64 of our message. That's the whole of the zip file. So hopefully, fingers crossed, when we look in our alert, there's certainly something in there. There we go. Okay, so we can see that Snort is actually is able to detect the malware in an email message. Okay, there is port 25. There's the machine we connected to. Then there's our machine there. Okay. Okay, so that's dynamic analysis, where we can actually use Snort to be able to detect the malware. Okay, so after static analysis and dynamic analysis, we then might do some sort of code analysis. So with this, what we're trying to do is we're trying to get back the original code. We're trying to analyze the way that it runs and to see what the behavior of the code actually is. So if it's a .NET or a Java application, it's fairly easy for us to disassemble the code because it's in a form that we can actually get back again. Okay, so let's run a disassembler. And let's see if we can open up a program. This is the exe that we're opening up. And we should be able to find that all the details of the code are actually embedded into the exe, so it's fairly easy for us to get the code back again and for us to be able to run it on a debugger. We can also use a program if the program is written in C++, such as IDA Pro, and with this we can actually have a look at the registers and debug the code as it's actually running. Okay, so let's run up. And this is our malware here. Okay, so we can add breakpoints in, so whether we can actually have a look at the code and the way it branches into each of the different areas. But in this case, here's the first few lines of it, and what I've done is added a breakpoint in, and then we might want to run the code, and we can see it's broken here. Shows you the registers that have just been changed, and these are all the registers here. So from here we can actually have a look at the memory, the threads that are generated, and so on, and then hopefully get some idea of how the code actually runs. So graphical interface, we can see where the code actually runs to and what it's actually doing. Okay, another program we can use is Visual Studio, where we can actually examine the code as it runs, look at memory, look at the disassembly, code, registers and stack, and so on. Okay, so this shows an example here. We have a C++ code, and we can actually run it. And put in breakpoints. And then we can look at the registers as they change. We can look at this disassembly. So for our exe, this is the machine code, the assembly language code, and this is the code, the high level code here. We can also look at variables and things like that. Okay, so this gives us some idea of how the code actually runs. Okay, so when the debugger runs, we actually see any changes in red here. Okay, so this shows an example of C++ code which has been converted into assembly language, and we use instructions such as move, that moves data from one place to the next. Interrupt will interrupt the processor and do something. Add and subtract, push and pop, we'll see in a little minute. Call allows us to call a function, return from it. Then we have basic operations such as compare, jump if equal, jump if not equal, and jump non-conditionally. So you can see that each of the high level commands that we have get converted into these machine code operations. So as we go through, the values actually change. So the IP is what's called the instruction pointer, and tells us where we should execute the code next. So when we're here, the IP says that we need to execute this line next. As we go through, then it says AC, which means this line, and so on. So the instruction pointer is important as part of the code. It tells us where we should be executing next. The other important one is the stack pointer. Stack pointer, as we'll see, is used to put values up onto the stack and take them off again. Okay, so when we see the execution of this one, this is the memory location of A, the memory location of B. So 1 goes into memory location of A, 2 goes into the memory location of B. We then take the memory location of A and we put it into the EAX register. There's 1. Now we're going to add whatever's in B to EAX, so we now get a value of 3. Okay, so we can see here how the processor actually steps through the code. So the registers that we have are AEX, which is a general purpose 32-bit register, and then we have stack pointer, SESI, the instruction pointer, and then the stack pointer. Okay, EIP is instruction pointer. An important concept is of the stack. With the stack, we push values onto the stack and then we pop them off. So it's a last in, first out type of approach. So in this case, we have some code. What we do is that we push our values onto the stack. The stack will do with the function will perform some operation, but what we want to make sure is that the values that we have back are the same as when we left the code. So we should be able to jump to this code here. We push the registers that we're going to use with inside the code onto the stack, and then at the end we pop them back off to make sure that all the registers are the same as when they left to call the function. Okay, so the push pushes onto the stack, and then the pop takes the values back off again. They should be taken off in the correct order. Okay, so this shows the stack area. The stack pointer identifies where we are in the stack, and then we push and pop the values back off. We have a shared memory inside our processor, our x86 architecture, where code and data share the same memory but have different end pointers. So apart from actually examining network traces and obviously the dynamic operation of the code, often what we have to do is we have to analyze the files in great detail. Either it's the content, the documents, or it's the fragments of data that are left behind. So let's have a look at one type of file, and that's we'll have a look at a flash file so that we can actually examine its content. Okay, so when we examine any sort of document type file, it normally has an extension. So a JPEG has a .jpg extension, GIF with a .gif. Each of these files is normally identified with this first starting few bytes, known as the magic number. So a GIF will typically start with a 47, 49, 46, 38 in hexadecimal or GIF89. So if we have a look at this, these are a number of magic numbers that we have. So for example, if we look at a GIF file, and here's an example here. Okay, so the first 3 bytes are these. So we'll have a look at the binary. We see here there's the GIF89A. And then what follows is normally a standard format that we can actually analyze. In this case, the GIF has things like the version number, the height and the width are the values that come next. So after these values, then in this case we have 2 values for the width, and so there's 3 values, and then the 8, 9 there, and this is these 2 values, the width and the height. So it's from these that we can actually determine some of the parameters of the files. Okay, 2 typical files that we often see and are used for malware are flash files, SWF or SWF at the FWS at the first 3 bytes, and PDF. So PDF will have a %PDF at the start. It's these 2 file types that are actually used to compromise the systems in the files that we'll look at later. Okay, so if we want to have a look at flash files. Here we are. So the first 3 bytes are FWS. Okay, so let's have a little bit more look in a bit more detail as to the things that come next, because it's obviously important that we can understand things like the version number and what some of the tags are on the file content. So when we look at a flash file, we should see FWS at the start. There is another type, and that's when we have a compressed header. So with a compressed header, we have at the start CWS. So we can see in this case we have CWS. What happens is that after this we actually have a compressed header. It is compressed with the zeblib format, compression format. So in this case, this web page will actually decompress the zeblib format, so it can be viewed in the same way as the other flash files can. Then the next byte that we have is the version number, and that's very important in Flash because certain compromises in Flash relate to certain values of the Flash content. So in this case, the 4th byte gives us our version number, and then the next 4 bytes gives us our file size, and it's defined in a little endian format. So this is the least significant byte, next most significant byte, and so on. So if we actually run our calculator, we bring up hexadecimal, so the value we have is 00002305. We convert that into decimal, and we get a value of 8965. Okay, so remember, for the Intel, it's little endian format. The smallest byte of the 32-bit integer comes first. If we're dealing with the old Mac type format, then it was a big endian, or the most significant byte was first. But most of the times, we deal with this little endian format. The values that come next will then determine the number of bits that we have for the format. So the next bytes will actually define the minimum x and the minimum y, and the maximum x and maximum y. So this whole line here is actually defining this. It defines the number of bits that we have in each of the x, y coordinates there. If you want to see this in more detail, then I've added the specification on the website. After this, we then get the frame rate. So that's how fast the frames. So Flash is a frame-based system where we have a number of frames, and then we'll move through the frames at a certain speed. So in this case, 0C is 12, so we have 12 frames per second. And then the next two numbers defines the number of frames that we actually have inside the package. After this, we have what are called data tags. And with this, we have a 10-bit identifier for the tag. So it might be defining the font, it might be defining a line, it might be defining an image, and so on. And these tags are well defined within the Flash format. And then the next bits define the size of the number of bytes that are used for that tag. Okay, so a tag number 9 defines that the background color is set, and in this case we're going to have 3 bytes. So this is set background color, and the red, green and blue, so that sets the background color to white. So when we when we look at our file, we can actually see there's the frame rate, there's the count. So if we can have a look at that one, that's what that actually looks like, and so on. So we can use a package to be able to reverse engineer our code. So we can also use a decompiler for Flash. In this case we have a package called Flasm, and we can disassemble our Flash code. So let's take this one and -d, we can see here that we can get all the basic script from the code. So that's as we saw before. There's the frames, frame rates, and so on. And then we have these tags inside the code, and then each tag has a certain ID. And we can see we can reverse all the Flash code from there. Okay, so it's a strong skill to be able to look at the files, file contents, and then to examine the byte details. One thing to notice here is a GFIF, which is actually a JPEG. So there's actually a JPEG file wrapped inside this Flash file, and FFD8 is a standard sign of start of a Flash, of a JPEG file. So let's look at an example exploit kit. So we'll be using the Phoenix 2 exploit kit, and we'll be looking at a couple of examples on how the malware writer creates the exploit. Okay, so there's three vulnerabilities that we'll actually have a look at, and we'll see how they work. Still one of the most popular is the CVE 2007-0071, and that uses an exploit in Flash Player 8 and 9 to be able to trigger a buffer overflow and compromise the system. So we'll see that with the load flash script. Then we'll look at CVE 2006-0003, and that exploits the ActiveX data object for MDAC 2.7 and 2.8, and it allows attackers to run some code on the system. And then the last one is the CVE 2010-08-06, which corrupts the memory on the system. Okay, so we'll have a look now at the exploit kit and how it actually works. But what we'll find is that it's all done in JavaScript. There's specially crafted PDFs and Flash content. The Flash content uses this action script here. The action script runs inside the Flash and is able to load up the malicious JavaScript. What will happen is that certain websites will be actually shown when the user calls up the site. Okay, so let's have a little look at the exploit kit. So here we go. So there's certain content in there, such as the Flash content. But we're going to have a look at the first one here, which is using Flash to be able to load up certain URLs. So we'll actually have a look at it here instead. Okay, so here's the main HTML file. Well, it's HTML, but really it's all JavaScript. So you can see from the start to the finish, it's just one big JavaScript. So the first exploit is this one. So when the script is run, so it'll run this, it'll run all these. It won't run this yet because it's a function, so it won't run any of these functions. It'll get to the end and it'll run this mdac. Okay, so that's how we read the JavaScript. So the first thing it's doing is to creating an object. So we have a look at it. It creates our with an ID of PDF. We then have this data here. So the first thing it's doing is creating what's called shell code. With the shell code, what happens is that this will execute an x86 opcodes here. So 53 I think is push, 50 is push also, and so on. So just like when we looked before, the assembly language code, these are the opcodes. So this is going to run some script actually on the machine. Okay, so so that loads up these three variables. We then run this mdac, because as we've seen at the very bottom, it runs mdac as a function. So when mdac runs, it will now create an object. This is our ID here, as we've done there for that object. It now runs the shell code. We create the shell code and actually tries to run this shell code on the system. That doesn't work. Then we then go. So it's trying to save that code into an exe and to run it. That doesn't work. Then it will call up this SWF function here. Okay, and this is where we're now calling up the flash. So the first one was a shell script. This one now is the one that will load up a link with inside the flash object in the browser. So what's going to happen is that these will get passed into the flash object, and we'll see how that happens in a little minute, but let's actually see what these are. And actually these are obfuscated links. So if we pull up our security website and we'll look at oops, let's do that again, and let's look at coding, and then we'll do our conversion. Okay, so this is the hexadecimal for this website. So what's going to happen is that this is actually going to load that website into the browser, and let's see if that site exists. It doesn't exist anymore, which is good. And we'll have a look at the next one. This is the next one. This is a directory. And there we go. So there's another website that will get called up. Okay, it's obviously been closed down now. Okay, and so we could do the same for all these things here. 20, looks like lots of spaces and so on. So this is going to create a new flash object. Okay, so there's the f data getting set to these values. Probably some sort of script that's going to happen with inside flash. Then what we do is load flash. Okay, so this actually creates the flash object. This is going to bring in flash. Okay, so flash will be then created. Now what happens is that with inside flash, someone has written action script. This is action script 3. So what should happen on frame 1, it calls up the interface, and then it will receive the JavaScript code from the interface. And there it is there. So the Flash itself then says, okay, call up the JavaScript. JavaScript then will then take this F data. The F data then gets passed into the action script and will compromise the Flash and will show the web browser page. Okay, so that's the second compromise that we have there. Okay, so again it tries to run the shell script again, and then if it doesn't do that, it'll try and do the Flash. And then the final vulnerability of this one is again it tries to run a shell script. So again, this is the shell script that will compromise the memory of the browser. Okay, so that's shown an example of our exploit kit, and this is still one of the most popular exploits around. So we've covered quite a lot of detail there. We've looked at some different code types in malware analysis. It's very important that really the analyzer can understand a whole range of software development environments, from high-level code to low-level debugging. Looked at some basic classifications, and hopefully in other of the presentations you'll be able to see some of these. And then we dived in to look at real-life malware. We looked at some static analysis where we can actually copy signatures, and then on to some dynamic analysis where we looked at the registers, the memory, the processes, and so on, and we could actually see what the malware actually did. And then went on to look at some code analysis where we can look at the machine code and how it actually runs, and how we can look at some disassembler. In other modules we'll be looking at this in more detail. And then we looked at some of the techniques that we might use to be able to forensically analyze some of the files that we're looking at, certainly to be able to look at the specifications for the file formats, and then to pick off each byte one by one and try and understand how the file has been created. And then we looked at some real-life malware, and we examined a real-life exploit kit. Okay, so other modules in this series will actually look in more details at some of these things. Thank you.